Okay, so sorry for the delay in getting this put up, but we're going to go ahead, or I'm going to go ahead and explain the homework from Chapter 10, since a lot of you asked for it, and it looked like several needed it. So let's just go ahead and describe each one of these. So the first problem is number 4, and what it says is if Michelson and Morley had detected an ether in their experiment, what implications would it have for the first postulate of special relativity? So if you go back to page 188, you'll see that the first postulate of special relativity is that the laws of physics are the same in all inertial systems. So if Michelson and Morley had been correct, what that would have meant was that there was a preferred direction in the universe, or a preferred reference frame that everything else could be measured relative to. And so that would have made the first postulate of special relativity invalid. And that's all that answer needed. Now the next one you had to do was number 8. And it said if an observer on the ground uses her own instruments to measure the speed of the light in question 7, will she obtain a value less than, greater than, or equal to c? Explain. So we know that c, I had some of you ask me this, that's just a variable that we use to mean the speed of light in a vacuum. So 3 times 10 to the 8th meters per second. So that's what c equals. Okay? And so the one thing to remember is that this speed of light remains the same no matter how the observer or the source is moving. Okay? So you saw this in the videos. You could have, for instance, a flashlight, and if we're in a vacuum, you know, it's putting out a beam of light, and then here's you on a ship. Don't make fun of my drawings. Here's a ship, and you're going towards the light. So even though you're going towards the light, so it would seem like the light is moving towards you faster. That would be kind of what we would normally think, right? We would think as we move towards the light must seem like it's going faster, or as we move away from the light must seem like it's going slower, but that's not the case. No matter if you're moving towards the light, if the light's moving towards you, if you're moving away from the light, you'll always measure the speed of light to be this 3 times 10 to the 8th meters per second in a vacuum. So the answer is that she would measure it to be equal to c. Alright? The next one you had was number 14. And that said, an observer on the train in figure for question 7 determined that firecrackers go off simultaneously in the engine and the caboose. How would an observer on the ground describe these events? So this is similar to one of the videos you watched. Instead of firecrackers, let's just talk about lightning bolts. So you have a person on a train, and you have a lightning bolt hit the front, and a lightning bolt hit the back. And then you have a person out here on the ground, and the train's moving this way. And you have a person on the ground watching it, okay? So if the person in the train thinks that these two bolts hit at the same time, then that must mean that the light from each one of them reached her eyes at the exact same time. But remember that she's going this way, okay? So that must mean that this back strike struck a little sooner because its light has to travel a little bit farther than this light. Remember that the light stays the same speed, but since she's moving this way, these light rays will hit her eyes a little bit sooner than light rays from back here. So in order for her to see both of these at the same time, this must have struck a little bit sooner from the perspective of this guy on the ground. Okay? So the guy on the ground would see the back lightning bolt hit before the front lightning bolt. Alright? So the best way to kind of always think about these problems is just kind of draw a picture and think about, well, what must happen for her to be able to see from this frame and from this frame. And there's that one video in the forum that I think really does a good job of kind of explaining this. So if this is kind of confusing to you, then make sure to go back and watch that video in the forum, because I think it does a pretty good job. So the next one is number 30. And it says, let me turn the page. Oh, actually, We can just skip number 30. If you have a question, I'm not going to test you over this. It's just talking about whether special relativity allows time travel into the past and into the future. So you can read it in the text. If any of you want more, just for your own personal knowledge, want to know more about it, then that's fine. Just email me and I'll shoot you back an answer. But you don't really have to worry about that kind of a question for the test. So let's go ahead and go to 32 actually. So 32 says, two events occur at different locations along a line perpendicular to the direction of relative motion. Will observers in both reference systems agree on the simultaneity of these events? Explain. Okay? So the key here, let's say we have a box. And let's say the box is moving this way. Alright? This is the key kind of thing that this is trying to get across. So what happens is, we know when this thing is traveling, the length of this box shrinks, okay? So it might look like this long when it's sitting still, and then shrinks when it's moving. But what do you notice? It only shrinks in the direction of movement. That's the key part, okay? So it's only shrinking along this axis because that's the way it's moving. It's not shrinking up and down. The directions that are perpendicular to the movement are not shrinking. So it's not like this and this are different. Those are both equal heights. Okay? Now what if you took this box here and you moved it this way? Right? Well then, this would shrink. You'd get some other value for the height, and this would stay the same. This would be the same as when it was at rest. Okay? So the key thing to remember is that the length contraction that makes the length shrink only happens in the direction of movement. Okay? And so that's what this question is trying to get across. And that's the key thing that you need to know for the test. The next one is 68. Okay. And it says, let me turn the page. What is the size of the adjustment factor for a speed of 25% that of light? So, I know a lot of you just looked this up in that table, but you actually need to know how to calculate this because I'm going to test you on a value that's not in the table on the quiz. So the adjustment factor is that gamma that you see in the chapter, and it's given, that's a V. It's given by this, so you can see that in the chapter. So the only variable in this entire equation besides gamma is V, okay? Because 1, 1, and C are all constants. So the only thing you're ever plugging into this is this V, alright? And so for this specific problem, it tells us we're going 25% of the speed of light. We can write this as 0.25 times c, right? Just converting a percentage into a decimal. So this is our velocity, or our speed, and we're going to plug that in right here. So let's go ahead and do that. 1 divided by 1 minus, our v is 0.25 c over c squared. Now c over c, that just is 1. Those cancel. Okay? So we're going to get 1 over 1 minus 0.25 squared. Okay? And 0.25 squared ends up being 0.0625. So let's go ahead and do that out, just so you can see all the steps. Okay? And then we just take 1 minus this, and you end up getting 0.9375. And then you take the square root of 0.9375, and you get 0.9682. And then you take 1 divided by 0.9682, and you get 1.03